Welcome back to another episode of Quick Chemistry. This is States of Matter. In our Introduction to Chemical Equations video, we saw how in chemical equations we have to indicate the state our reagents and products are in. We represent chemical species in the solid state by writing an S in brackets, those in the liquid state by writing an L in brackets, those in a gaseous state with a G in brackets, and those which are aqueous, or dissolved in water, by writing an AQ in brackets. In today's video, we're going to look at what it means to be solid, liquid, or gaseous, while leaving aqueous solutions out for another video. Before we start, let me begin by defining what I mean when I refer to a chemical species. A chemical species is a broad term used to describe any set of atoms or molecules which are chemically identical. I'm going to use this term, which I often shorten simply to species in this and future videos, since it's a nice umbrella term for chemically identical groups of atoms or molecules without having to specify whether what I'm referring to is an atom, molecule, compound. Additionally, I use the term particle to refer to any individual atom or molecule belonging to a chemical species in any state of matter. In this video, particles of any given species are drawn out as spheres. Now that that's out of the way, let's officially kick this video off by looking at the kinetic theory of matter. States of matter are defined by what's called the kinetic theory of matter. This theory recognizes that the average kinetic energy of a set of particles, where kinetic energy refers to the energy that particles have because they're moving about, directly relates to the temperature of their surroundings. The hotter the temperature, the more energy the particles have. When we say that particles are in the solid state, they have a very low average kinetic energy. The particles are packed tightly together, and the only motional movement that they really exhibit is when they vibrate in place next to one another. Solid state matter has a fixed shape and fixed volume, like an ice cube. We can melt species in the solid state to obtain a liquid. If you think about melting an ice cube, you do so by heating it up, which is the equivalent of giving the water molecules more kinetic energy until they form a liquid. In a liquid, particles are more spaced out, and the individual particles exhibit more motion. They can slide over one another and will conform to take the shape of the container. Species in the liquid state have a fixed volume, but no shape. It's like filling a pot with water from the tap. The water molecules disperse to take on the shape of the pot, but the volume within the pot is limited to how much water you pour in. Now imagine we begin heating this pot of water on the stove. By heating the water, we're giving the water molecules even more kinetic energy, such that some of them will form water vapor. That is, they will become a gas. Gaseous particles have a far greater average kinetic energy than solids or liquids, and their particles are very spread out. The particles move freely throughout the space they're in, and they have no fixed shape or volume. Out of the three most basic states of matter, solid, liquid, and gas, gaseous particles have the greatest kinetic energy. It's important to note that matter changes states reversibly. In the above example, we looked at two basic processes: melting to describe a movement from a solid to a liquid, and boiling to describe a movement from a liquid to a gas. We can also get the reverse of these processes happening. To get from a gas to a liquid, we get what's called condensation. This is where some of the kinetic energy of gaseous molecules is lost, usually as heat moves to the environment, such that we get liquid particles forming. This is what happens when you're showering with steaming hot water and end up with water droplets on the bathroom mirror or tiles afterwards. While you're in the shower and the environment's warm, gaseous water molecules, steam, spread throughout the bathroom. When you get out of the water and after the room cools down after some time, many of these gaseous steam particles lose sufficient kinetic energy such that they condense into liquid droplets on the surfaces of your bathroom. We can also get transitions from liquid to solid by freezing liquids. It's like when you make ice cubes by putting water into the freezer. After enough time in the sub-zero temperatures of the freezer, the water molecules lose enough heat such that their average kinetic energy decreases to the extent that they form a solid, ice. We can also skip moving through the liquid phase entirely. We can move directly from solid to gas in a process called sublimation, and back from gas directly to solid in a process called deposition. Storing dry ice at room temperature is a great example of sublimation. Dry ice is frozen carbon dioxide, which is a gas at room temperature. If we get a block of dry ice and leave it in a normal room, say in the middle of a dining table, it'll look like it's disappearing, since it changes directly from a solid to a gas, by subliming, without moving through the liquid carbon dioxide phase first. Deposition is the reverse of this. It's the conversion of a gas to a solid without moving through the liquid phase first. An example of this is when you get frost forming on windows on very cold days. When gaseous water molecules on the inside of a warm home come into contact with a freezing cold window pane, they form a frost on the glass. This happens because they're transitioning from the gaseous state as moisture in the air into a solid state, frosty ice, on a window pane. And that's it for this video. Here's a helpful diagram that nicely summarizes what we've covered today, with red arrows representing the addition of heat and blue arrows representing cooling. As always, if you found this video helpful, please like and subscribe and comment down below if there's anything else you'd like me to cover. Until next time.